You think you know what an atom looks like. You've seen the pictures. A tiny nucleus at the center, electrons whizzing around it in neat circular paths like planets orbiting the sun. Clean, simple, understandable. That image is in every textbook, every science museum, every documentary about the microscopic world. Here's the problem. That image is a lie, not a simplification, not a helpful approximation, a fundamental misrepresentation of what's actually happening inside every atom in your body right now. Electrons don't orbit. They never have. They can't. And once you understand why, once you see what's really going on, you'll realize that matter itself is far stranger than anyone ever told you. Let me show you what I mean. Let's start with what you think you know, the planetary model. Rutherford gave us the nucleus in 1911. Bohr added the orbits in 1913. Electrons circle the nucleus like tiny moons. Each orbit is a specific distance from the center. Electrons can jump between orbits, but they stay in their lanes. Neat, predictable, wrong. Here's why that model is impossible. An electron has charge, negative charge, and when a charged particle moves in a circle, it's accelerating, always. Even if it's moving at constant speed, the direction is changing, which means the velocity is changing, which means it's accelerating. And here's the thing, Feynman understood cold. Any accelerating charged particle must radiate energy. Must. This isn't a suggestion. This is Maxwell's equations. This is electromagnetism. When you shake a charge, you create electromagnetic waves. Radio antennas work on this principle. You wiggle electrons up and down a metal rod and boom, you're broadcasting. So if an electron is orbiting, it's accelerating. If it's accelerating, it's radiating energy. And if it's radiating energy, it's losing energy. And if it's losing energy, the orbit gets smaller. The electron spirals inward. Fast. How fast? Do the calculation. An electron orbiting a hydrogen nucleus would radiate away all its energy and crash into the nucleus in about 100 millionth of a second. 100 millionth of a second. Atoms should collapse instantly. Matter should not exist. You should not exist. But here you are, reading this, made of atoms that have been stable for billions of years. This should break your brain. The planetary model predicts that all atoms self-destruct immediately. But atoms don't self-destruct. So the model is wrong. Not approximately wrong. Catastrophically, fundamentally wrong. This was the crisis of physics in the early 1900s. Classical mechanics said atoms can't exist, but atoms obviously do exist. Something was deeply, profoundly broken in our understanding of reality. Feynman understood what this meant. You can't patch this problem. You can't add a little correction factor and make it work. The entire framework is wrong. You need a completely different way of thinking about what's happening inside an atom. Enter quantum mechanics. Now, most people hear quantum mechanics, and they think it's just weird physics for small things. They think it's regular physics with some probabilistic fuzziness added on top. No. Quantum mechanics isn't regular physics plus uncertainty. It's a totally different description of reality, and at its core is something Feynman spent his entire career trying to get people to understand. Electrons aren't particles that orbit. They're not little balls tracing paths through space. They're quantum objects, and quantum objects don't have positions in the way you think they do. Let me say that again because it's crucial. An electron inside an atom doesn't have a position. It doesn't have a trajectory. It's not times somewhere, times moving, in times some direction, asterisk. Those concepts don't apply. What does an electron have? A wave function. The wave function is not a physical wave, like a water wave or a sound wave. It's a mathematical object that describes the probability of finding the electron in different places if you look. But here's the thing Feynman was obsessed with. Until you look, the electron isn't hiding in one spot. It's not that you just don't know where it is. It genuinely doesn't have a definite position. The electron is smeared out. It exists in a state of superposition, occupying many places simultaneously. This is not poetic, this is operational. This is what the math tells us happens, and every experiment we've ever done confirms it. For a hydrogen atom, the ground state electron isn't orbiting the nucleus. It's existing as a cloud of probability centered on the nucleus. There's a higher probability of finding it here, lower probability there. But it's not tracing a path. There is no path. Feynman loved to emphasize this. He'd say, don't ask where the electron is. Ask what happens when you measure where the electron is. Those are completely different questions. If you do an experiment to detect the electron's position, you'll find it in some specific location. But before the measurement, it was in all those locations at once, weighted by probability. The act of measuring forces it to choose a position. This drives people crazy. They say, but surely the electron was really somewhere, and we just didn't know where. No. Every test we can devise says no. The electron was not in a definite position before measurement. Position itself is created by the measurement. This is what Feynman meant when he said, I think I can safely say that nobody understands quantum mechanics. Even he, one of the architects of quantum field theory, was humble about the weirdness. You can learn the math. You can use it to make predictions. You can win a Nobel Prize. But understanding in the intuitive sense, that's gone. You have to rebuild your intuition from the ground up. Now, let's talk about what actually determines where an electron can be found. If it's not orbiting, what keeps it near the nucleus? What structure does an atom have? The answer is energy levels and wave functions. Think about a guitar string. When you pluck it, it vibrates. But it can't vibrate at just any frequency. The wavelength has to fit between the two fixed ends. You can have 1/2 wavelength fitting on the string, or 2/2 wavelengths, or 3. But you can't have 1.7 half wavelengths. The ends are fixed, so only certain patterns are allowed. Those allowed patterns are called modes. Each mode has a specific frequency, a specific energy. Electrons in atoms are similar, but in 3 dimensions. The electron's wave function has to fit around the nucleus in a way that's self-consistent. Only certain wave patterns work. Each allowed pattern corresponds to a specific energy level. The lowest energy level, the ground state, has the electron's wave function concentrated near the nucleus. Higher energy levels have more complex patterns, nodes, regions where the electron is never found. Feynman showed how these patterns emerge from the Schrödinger equation. You solve the equation for an electron in the electric field of a nucleus, and out pop these discrete solutions. These are the orbitals. Not orbits, orbitals. Regions of space where there's a high probability of finding the electron. An s orbital is spherical. A p orbital has 2 lobes. A d orbital is even more complex. These aren't paths, they're probability clouds. They're standing wave patterns. And here's the beautiful thing. Because these are standing waves, they don't radiate energy. They're stable. An electron in a stationary state doesn't accelerate in the classical sense, so it doesn't radiate. The crisis is resolved. Atoms are stable because electrons aren't moving in the way we thought they were moving. This is what Feynman discovered about reality. Not just about electrons, but about everything. At the quantum level, particles don't have definite trajectories. They exist in superpositions. They're described by wave functions. The world is fundamentally probabilistic, fundamentally uncertain, fundamentally weird. And you can't escape this weirdness by saying, well, that's just for tiny things. No, you are made of atoms. Your body is quantum mechanical. Every chemical reaction in your cells, every neural firing in your brain depends on electrons doing this quantum dance. The reason chemistry works, the reason molecules form bonds, is because electrons from different atoms can share wave functions. The electron clouds overlap. The electrons aren't particles exchanging between atoms. They're waves that can be delocalized across multiple atoms simultaneously. When 2 hydrogen atoms form H2, the electrons aren't orbiting their individual nuclei anymore. They're in a molecular orbital that encompasses both nuclei. They exist around both atoms at once. This isn't a metaphor. This is what creates the bond. Everything solid you've ever touched exists because of quantum mechanics. The reason this table doesn't collapse is because the electron wave functions in adjacent atoms repel each other when they overlap too much. It's all electromagnetic force, yes, but mediated by quantum wave functions. Feynman had a way of getting to the heart of this. He'd ask, how do you measure whether an electron is orbiting or not? You can't. There's no experiment that detects an electron following a path, because it's not following a path. Every experiment you can do is consistent with the electron being a spread-out quantum wave that occasionally manifests as a particle when you measure it. And this leads to something Feynman was famous for, his path-integral formulation of quantum mechanics. In classical physics, a particle goes from point A to point B along one specific path. In quantum mechanics, Feynman showed that the particle takes all possible paths simultaneously. Every single path from A to B, no matter how weird, contributes to the wave function. Some paths contribute positively, some negatively. Most cancel out. The ones that survive, that add up constructively, are the ones we observe. This isn't just a mathematical trick. This is what experiments show. In the double-slit experiment, an electron going through two slits interferes with itself. How? Because it went through both slits. It took both paths. Its wave function split, went through both openings, and recombined on the other side. One electron, two paths, simultaneously. Feynman understood that this is the operational reality. This is what nature does, and you either accept it and learn to calculate with it, or you spend your life being confused. Now, here's where it gets even stranger. The uncertainty principle. Heisenberg's uncertainty principle says you cannot simultaneously know the exact position and exact momentum of a particle. Not because your instruments aren't good enough, not because the particle is too small to measure without disturbing it, but because position and momentum are fundamentally incompatible properties. The more precisely you know where an electron is, the less precisely you can know how fast it's moving. This is built into the wave function. It's a mathematical necessity. Why? Because position and momentum are related by a Fourier transform. A wave that's localized in position must contain many different frequencies. A wave that has a single frequency must be spread out in space. You can't have both. Feynman loved this. He'd point out that this isn't a limitation of measurement. This is a statement about what can exist. An electron cannot have both definite position and definite momentum. Nature doesn't allow it. And this, finally, is why electrons don't orbit. An orbit requires both a definite position, the electron is here on the orbit, and a definite momentum, it's moving in this direction at this speed. But you can't have both. The uncertainty principle forbids it. What you have instead is a stationary state where the electron's probability distribution is constant in time. It's not moving. It's not going anywhere. It just is, existing as a cloud of possibility. Think about how extraordinary this is. You learned in school that electrons orbit like planets. That mental picture is in your head right now. But that picture is completely, utterly wrong. The truth is that electrons don't move in the sense you understand movement. They exist in quantum states. They're probability waves. They're delocalized. They don't have trajectories. And this isn't some arcane detail about atoms. This is the foundation of all chemistry, all biology, all material science. The periodic table, the structure of DNA, the conductivity of metals, the color of light emitted by stars. All of it comes from electrons existing in quantum orbitals, not orbits. Feynman spent his life trying to make people see this, not just accept it as a formula, but really see it. He developed quantum electrodynamics, showing how photons and electrons interact by exchanging virtual particles, by exploring all possible paths through space-time. He won the Nobel Prize for this work. And the whole time, he insisted on operational thinking. Don't ask what the electron is. Ask what the electron does. Ask how you measure it. Ask what predictions the theory makes and whether experiments confirm them. And every experiment confirms quantum mechanics. Every single one. We've built transistors, lasers, MRI machines, atomic clocks, quantum computers, all based on the understanding that electrons don't orbit. We manipulate individual atoms with scanning, tunneling microscopes, using quantum tunneling effects that only make sense if electrons are waves. The technology in your phone right now depends on quantum mechanics being true. Semiconductor physics is entirely quantum. The electrons in the circuits aren't little balls bouncing around. They're quantum waves flowing through energy bands. You're holding applied quantum mechanics in your hand. And yet, people still imagine electrons orbiting because that's the comforting picture. That's the one that makes sense. That's the one that fits your intuition. But your intuition is wrong. Your intuition evolved to deal with macroscopic objects moving at slow speeds. It did not evolve to understand the quantum world. So when you encounter quantum mechanics, your intuition screams that it's impossible, that things must have positions, that they must follow paths. This is the gift Feynman gave us, the insistence that we face reality on its own terms. Not comfort, not familiarity. Truth. The truth is that electrons are quantum objects described by wave functions that evolve according to the Schrödinger equation. They don't orbit. They exist in superpositions of position states weighted by probability. They tunnel through barriers. They interfere with themselves. They're entangled with other particles across arbitrary distances. This is reality. This is what the universe is actually made of, not tiny solar systems, not particles on rails, but quantum fields and probability waves and fundamental uncertainty. And the fact that we figured this out, that we can calculate it, test it, use it, that's one of the greatest achievements of human intelligence. So next time you think about an atom, don't picture electrons orbiting. Picture a nucleus surrounded by clouds of probability. Picture wave functions with complex three-dimensional shapes. Picture quantum states that don't have classical analogues. Picture what Feynman saw, the real structure of matter, the quantum world that underlies everything you touch and see, not orbits, not paths, not comfortable mechanical pictures. Truth.